Hello and welcome to the third video podcast on capacitors and capacitance. In this video, we're going to look at how do we charge a capacitor and what graphs can we draw to illustrate how a capacitor charges. We're also going to start to look at how does a capacitor discharge, and that will be covered more in the final and fourth video podcast. So first of all, how can we charge a capacitor? Well, we looked in the first two videos about how a capacitor charges. There are two ways to do this. We can either charge a capacitor through a fixed voltage, as we saw in the first two videos, or we can charge a capacitor using our constant current. First, let's look at how we can charge a capacitor through a fixed voltage. If we look at the charge time graph for a capacitor that is charging, you can see how the charge at the beginning, the charge is 0 and it increases very rapidly, and then it starts to increase less rapidly until it starts to increase very slowly, and then by the time it's reached its maximum charge, it's decreased to 0. The gradient, the rate at which it's charging, has decreased to 0, so it's stopped charging and it's reached its maximum charge. This graph shows an exponential type curve. The charge builds up on each plate, the same charge builds up on each plate until it reaches the maximum value Q max. And we know that depends on the battery EMF, V0, and the capacitor of the capacitor C, because Q max equals C V0. And if we look at the rates of charging, how quickly it charges with time, we're going to look at delta Q over delta T, and we know that that equals to the current. So the gradient of this graph is equal to the current. And the gradient starts off at a maximum current, and it decreases. The gradient is decreasing all the way up until the gradient becomes 0 as the curve flattens out. And that's saying that the current is maximum to start with and decreases to 0 over time. And at that point, the potential difference across the plates is equal to the potential difference of the battery. Now, how do we charge a capacitor using a constant current? Well, this is a bit more difficult. It's a bit more complicated. We need to use a variable resistor to be able to control the current flow and keep it constant. If we look at this circuit here used to charge a capacitor at a constant current, we can see there's a variable resistor in series with the capacitor. Variable resistor must be set to high for a high resistance when the current starts to flow. So this keeps the current from being too much to start with, and as the current would start to fall, we can decrease the resistance of the variable resistor. And this way we can keep the current constant. And if we draw a charge time graph for this particular situation, we can see that the charge now increases at the same rate throughout the charging of the capacitor. And we know the current is equal to the gradient. The gradient is now constant because we have a straight line and showing that we've got a constant current. So the current is neither very high to start with, and then it doesn't decrease very slowly to 0. It decreases. The current is constant throughout as the charge builds up. The current doesn't decrease at all, but the charge accumulates at the same rate. So the current kept constant, the capacitor charges at a constant rate. We're going to start to look at how does a capacitor discharge. Well, when a capacitor discharges, the stored energy, a stored charge on the capacitor is then used to form a current which provides energy to a circuit. We have to first disconnect the capacitor from the battery and then connect it to a circuit with a resistor or device that will use the flowing current. There is an animation here, which I recorded separately. I didn't work out recording it with a video. So I suggest you look at the video recording of this animation to see a capacitor charging and then having to link the capacitor to a different circuit to see it discharging. This is the circuit diagram for the capacitor charging. We put the switch to A so that the battery here is linked to the capacitor, and the charge flows from the battery onto the capacitor and from the other plate round. So that's the way we charge the capacitor. To discharge the capacitor, we need to move the switch to B, so that then the charge that is stored on the capacitor will start to flow around the lower circuit. We can use a voltmeter to measure the capacitor voltage here as it discharges. There's another animation to show you how you can change the switch from the charging circuit to the discharging circuit and measure the voltage across a resistor, voltage across the capacitance when it's connected to a resistor. So we know the capacitor is fully discharged when the potential difference across the capacitor is 0 and the current is also 0. So when all the charge has left the plates, the potential difference across the plates of the capacitor will be 0 and no more current will be flowing in the bottom circuit. In the discharging circuit, the lower circuit here, when the switch is close to B, some of the energy from the current is dissipated in the resistor, and the resistance controls the flow of charge, so it can control the current. So depending on what kind of resistor we have, if we have a very large resistor, then how do you think that will affect the rate of discharging? A large resistor will lower the current, and therefore it will take longer to discharge the capacitor. So a large resistance will decrease the rate of discharging, decrease the current. A small resistance, it will increase the rate of discharging. So we'll have a high current, but it will discharge much more quickly. Let's look at a charge time graph for a capacitor discharging. You can see that the charge is maximum to start with, and it decays exponentially. So it decreases exponentially. The charge decreases until it will eventually reach 0. So we know that an exponential decay graph will never actually reach 0, but in real life, the charge is actually a discrete data, it's not continuous, and so there will be a point when the charge has actually reached 0. That's the charge time graph for capacitor discharge. We know that the drop in current, which is the rate of loss of charge, is going to be proportional to the drop in voltage because the resistance is constant in the discharging circuit. That's the end of the slides. Please answer quiz 3, and then move on to the next slide.